I mean, creating a fully reusable orbital rocket is one of the hardest engineering problems ever. It's certainly, a candidate for most difficult engineering project ever. It's on the podium at least.
That's a powerful statement from the person leading the spaceflight revolution. So, why is building Starship so astonishingly difficult? What elevates it to the podium of humanity's greatest engineering challenges? To truly understand, we have to look past the fire and steel and dive into the fundamental problems that SpaceX is working to solve. First, we need to define the term that changes everything: full reusability. This is the core principle that sets Starship apart from everything that has come before. We've grown accustomed to the incredible achievements of the Falcon 9 rocket, which is also reusable, but that is partial reusability. Falcon 9 made history by landing and reflying its first stage, the largest and most expensive part of the rocket. However, its second stage, after delivering its payload to orbit, burns up and is destroyed during re-entry. Starship is a different beast entirely. Full reusability means that both the Super Heavy booster and the Starship upper stage must return to Earth intact, ready to be refueled and reflown in a very short amount of time. This represents a quantum leap in difficulty. A Falcon 9 booster separates at an altitude of around 70 kilometers and a speed of roughly Mach 6. The Starship upper stage, however, must shed the velocity of orbit, a blistering 17,500 miles per hour, or Mach 25. The thermal and aerodynamic forces involved aren't just a little bit higher. They are an entire order of magnitude more severe. The kinetic energy that must be dissipated as heat during re-entry scales with the square of the velocity, making the challenge of recovering an orbital second stage exponentially harder than recovering a first stage booster. The reward for solving this puzzle is Starship's other game-changing advantage: its colossal payload capacity. Musk has confirmed what the next operational version of the vehicle will be capable of.
It's capable of over 100 tons to orbit, fully reusable. And I think unless we have some very major setbacks, SpaceX will demonstrate full reusability next year, catching both the booster and the ship, and being able to deliver over 100 tons to a useful orbit.
100 metric tons. Let's put that number in context. The Space Shuttle, a marvel of its time, could haul about 24 tons to low Earth orbit. The Falcon 9, in its reusable configuration, carries around 17 tons. Starship doesn't just offer an incremental increase, it offers a transformational capability. This isn't just about launching bigger satellites. It's about launching entire space station modules, massive deep space telescopes, and the building blocks for a permanent base on the moon, all in a single go. However, to achieve this incredible capability, Starship must overcome a challenge so immense it has been called impossible. A problem that even NASA, with all its resources, never truly solved: the heat shield. Why is a reusable heat shield so impossibly hard? First, it must be rapidly and reliably reusable, a feat no orbital spacecraft in history has ever accomplished. NASA's Space Shuttle was an engineering marvel with a reusable thermal protection system. But after every single flight, it required a staggering 9 months of meticulous inspection, repair, and tile replacement. This 9-month process was a monumental undertaking. It involved detailed thermal imaging scans of the entire orbiter, painstaking pull tests on thousands of individual tiles to check their bonding, replacing damaged gap fillers, and re-waterproofing the entire system with millions of tiny injections. An army of technicians would spend thousands of hours poring over every single tile, looking for chips, cracks, and signs of wear from micrometeoroid impacts or the stresses of flight. It was a process that demonstrated reusability was possible, but also proved it wasn't yet practical or affordable. For Starship's vision to work, turnaround needs to be measured in hours or days, not months. The material science and engineering problem of Starship's heat shield is a list of seemingly contradictory requirements. It must survive scorching temperatures, The shield has to protect the ship from the 1,400 degrees Celsius furnace of atmospheric re-entry. This isn't just friction. At Mach 25, the vehicle is moving so fast that it creates a powerful shockwave, compressing the air in front of it to the point where air molecules are ripped apart and ionized. This process, known as dissociation, is what creates the glowing plasma sheath, a state of matter hotter than the surface of the sun. It must be incredibly lightweight. In rocketry, mass is everything. Every gram dedicated to the heat shield is a gram that cannot be dedicated to payload. The tiles are made primarily of silica fibers, making them mostly empty space, feeling almost like styrofoam to the touch. Yet they must be incredibly robust. It must be a perfect insulator. This insulation challenge is one of the most extreme in all of engineering. The tiles must simultaneously reject the 1,400 degrees Celsius plasma on the outside, while protecting tanks holding liquid oxygen at -183 degrees Celsius and liquid methane at -161 degrees Celsius. That's a temperature gradient of nearly 1,600 degrees across just a few centimeters of material. A failure here wouldn't just be a problem, it would be a catastrophe. It's a system of thousands of unique parts. The shield is comprised of approximately 18,000 hexagonal silica tiles. Each one must work flawlessly with its neighbors, forming a near-perfect thermal barrier with no critical gaps. Managing a system of 18,000 individual parts, each a potential point of failure, is a staggering logistical and engineering challenge. The stakes are impossibly high. As the history of the Space Shuttle program taught us, a gap between tiles that is just a fraction too wide, or a tile that fails under the stress of re-entry, could allow superheated plasma to penetrate the hull, leading to the loss of the vehicle. And above all else, unlike the Space Shuttle, these tens of thousands of black ceramic tiles must perform their life-saving duty, flight after flight, with minimal inspection and refurbishment. That is the critical difference between a reusable prototype and an operational, interplanetary transport system, as Elon Musk stated it himself.
For full reusability of the ship, there's still a lot of work that remains on the heat shield. So no one's ever made a fully reusable orbital heat shield. Like the shuttle heat shield had to go through 9 months of repair after every flight.
He then distilled this monumental challenge down to its essence.
And is that a material science problem, or is that an engineering problem, or both?
Yeah, I mean, it's a material science engineering problem. So it's...
Starship is not just a bigger rocket. It is an extraordinary machine, being designed to operate at the very edge of what physics allows, where steel glows white-hot and the air becomes a fiery plasma. Every test flight we witness isn't just about how high it can go. It's a brutal, real-world test of those 18,000 black tiles. Each one a small but critical piece of one of history's greatest engineering puzzles. But why go to all this trouble? Why build such a complex and expensive machine to solve a problem this difficult? The answer isn't about launching satellites or reaching Earth orbit. The answer lies much, much further away. Join us in part 2 as we explore the grand vision behind Starship.